So in this section, we're going to look at what happens when we don't know the distribution of x. Can we still estimate the mean and variance of y? Right, so it turns out that the minimum information is that we need to know the expected value of x and the variance of x. Okay, so given these two things, which are fairly easy to estimate, so we only know the mean and variance of x, and there's a function y equals g of x, right? All right, so turns out we can do this approximation using Taylor series. Now, this is the Taylor series approximation. So hopefully you remember it from calculus, right? So this is the 0th order, 1st order, and 2nd order approximation, right? And then you have more terms. All right, so what we're going to do is always use the second approximation for the mean of y. All right, and the reason is because if we take the first order approximation, we would fall within Jensen's inequalities problem. So let's take a look at that. All right, so first of all, let me take expected value of that equation up here. So we're going to take the expected value of y, right? If I'm able to write. Okay, expected value of y. So expected value of g of x, really. Expected value of all this thing. Okay, so when I do the expected value of this term, so we're going to apply expected value to each term. So expected value of this term, it's a constant, right? Because the function g is a constant and mu is a constant. Mu is just the mean of x. So this term remains unchanged. Now, when I take the expected value of this term, okay, the g prime is a constant, so it's going to come out, and I'm going to get g prime, and then expected value of x minus mu. Right? And that's going to be 0, right? Because this is going to be the expected value of x minus mu, right? Everything times g prime. But these are one and the same, so they cancel out. So this term is going to be 0. And now when I take expected value of this term, I'm going to have 1/2 g second expected value of x minus mu squared, which hopefully you recognize it by now. This is the variance of x, sigma squared. Okay? And that's how we come up with this equation, which is the expected value of y in the second order approximation. Okay, so we're going to take the function evaluated at the mean of x, right? And we said that this term was the lazy approach. Remember g of a of x? G of mu is the same. So the second term right here is a correction for the bias. And remember we said when the function was linear, then it doesn't matter which one you use. Same thing here, or now you can see why. Because for a linear function, the second derivative is 0, so this term is 0. But if it's nonlinear, this term would be the correction for that bias. Okay, so unless your function is linear, equation 5.4 is the one to use. Okay, now for the variance, turns out that we always take the first order approximation for the variance, right? Now let me show quickly how we do this. As the same thing, we're going to take the variance of y up here, and then you see what's going to happen. Oh, sorry, I'm done. Let me pause it. Right, so if we take the variance of y up here, we're going to get the variance of a constant, that's going to be 0. Then we're going to have the variance of this term, okay? So let's work it out. The variance of the whole thing. G prime is a constant, so it's going to come out squared. So G prime at mu squared times the variance of x minus mu. Okay? And the variance of, remember the variance of ax plus b is just a squared variance of x, remember? So that's what we're going to use here. Here we have x minus mu. So the variance is going to be the x, a is 1, right? So it's just going to be the variance of x, because a is 1 in this equation, right? So that times the variance of x sigma squared, which is what we have here. Now, why do we not consider this term? Is because when you take the variance of this term, then you're going to get the g second term squared, the 1/2, right, squared 2, so let me put it here, and then times the variance of x minus mu squared, like that. Okay, it turns out that this term requires to know a lot more information than we have. We only have the variance, but if you work out what this is, right, it's x squared minus, 2x, etc., plus mu squared. You see, we're going to have the variance of these terms, right? But there might be a covariance between x squared and x, so there will be a covariance, so you would need to have that too. And then there are higher order terms that will appear, and in general, we don't have enough information to evaluate it, right? So at least we would need the covariance of x squared and x, I guess. But in general, we always use the first order approximation for the variance. So g prime squared times sigma squared. Very good. All right, so as an example, let's do this one. Okay, so this is an earlier example, actually. So, because I don't have examples for this section just yet. So let's say it's the same thing, right? But so we don't know that x is exponential. All we know in this case is that e of x is 1 over lambda. Okay? And also the variance of x is 1 over lambda. Okay, so in this example, we have this function, and also all we know about x is the mean and variance, right? And let's see how we do. So, and the question is, what is the expected value and variance of y? Okay, so for the expected value of y, we apply the formula. So first is the lazy approach, the lazy approach. So it's evaluating the function e3e to the x, and instead of x, we're going to plug in the expected value of x, so 1 over lambda. Okay? That's the first term. And then comes the correction. Remember, it was 1/2 times the second derivative, right? So, in this case, g prime of x, what is it? 3e of x. Yeah, well, they're all the same, right? Also, g second of x is 3e of x. Yeah, they're all the same. All right, so 1/2, the second derivative, 3 times e of x. So again, we evaluate always at mu, so at the expected value of x. which is 1 over lambda, and this guy goes squared. Okay, so in this case, that would be your best approximation for the mean. I would be interested to compare with the mean that we get with the exact, because here we know I might have that for the lecture. All right, and for the variance, we're going to use this first order approximation for the variance. And the formula was the first derivative squared times the variance of x. Okay, so the first derivative in this case is the same as 3e of x. Now instead of x, it's always 1 over lambda in this case, because that's the mean. Okay, so that's g prime of x squared times the variance of x, which is also 1 over lambda in this case. Right? So this would be your second order approximation for the mean, first order approximation for the variance for this problem. All right. Yeah, so these formulas, right? Very good. So nice and easy. Let's just extend this for several random variables. So y is going to be a function of all these x's, right? The vector x, we know it. And now we're going to assume that we don't know the joint PMF, right? But we do know the mean, the variance, and covariance, right? So we know the covariance matrix and the mean as usual. Okay, so in vector notation, the Taylor series can be written like this. So very nice. Almost the same as the other one. Now, these G and H are famous matrices. So G is the gradient vector, and H is the Hessian matrix. So the gradient is just a vector of first derivative. The Hessian is of second derivatives. Do I have the definitions? No. But you get it, right? So G, let me just spell it out real quick. G is going to be a vector, right? So here you're going to have all the partial derivatives. dg, dx1, dg, dx2, etc. Okay, and the matrix, the Hessian, is a big matrix. Right, so here you have d2g, dx1 squared. Right next to it is d2g, dx1, dx2, etc. So in the diagonal, you're going to have all the second derivatives, and on the up diagonal, you're going to have all the cross derivatives, which should be symmetric too. Right? Sorry about the confusing notation. Okay, so we apply the same method. We're going to take expected value to the second term and variance to the first term, right? And these are the equations for the expected value. Now the first line, it's a little cryptic, but it's not a nicer vector notation. All right, so yeah, don't worry about it. I guess you can read explanations here, but let's focus on, I think the third one is the most useful, right? And it's very similar to the variance of linear combinations we saw before, all right? Okay, so the second order approximation for y so it starts the same, is the function evaluated at the mean, right? That's the lazy approach. And remember, the mean is a vector now. All right, and then we have the correction, right? So 1/2. And here is the sum of all the diagonal terms on that matrix, on the Hessian matrix, right? So you have all the second derivatives and then times the variances of each variable. Okay, and then we have the off-diagonal terms. So you have the covariances, and then you have the cross derivatives. And remember, look at, so here we're doing the summation over the upper triangular matrix, right? Same as we did with linear combinations. Now, the reason you don't see a 2, right, before we had a 2 and this double summation of covariances, is because we have this 1/2 at the beginning. So it kind of cancels it out. All right. So these are the formulas we obtain. Oops, sorry about that. What did I do? Okay. These are the formulas. Now, when these guys are independent, all these go to 0 as usual, right? Because the covariance would be 0. Okay, and then the first order approximation for the variance would be just the second term, remember? In this case, this is the second term, so we have the gradient vector times the covariance matrix. Okay, and it simplifies to this. So it's just the sum of all the first derivatives squares times the variances. All right, let's do an example. This can get a bit, it's not difficult, but it's, what's the word? Tedious. Tedious is the word. Okay. So here we have this relationship between random variables. So H is the hydraulic loss, and it's a function of all these, the pipe length, flow velocity, etc., etc. All right? So for all these random variables, we have their means and coefficients of variations. Okay, so the mean of V is 10 and coefficient of variation 15%. All right, and then the question is approximate the mean and variance, just knowing this. All right, so these are the values we get. So here's mean and sigma, standard deviation, right? Which is just coefficient of variation times the mean, which is all we need really. The other thing we need is the gradient and Hessian matrix, right? So here is the gradient, and it has these 5 components. Let me break it down for you. So that's 1, 2, 3, and 4. 4 components, I guess, right? Okay. So the first one is the derivative of this function h. Oh, we have 2 h's. One's the Hessian and one's this. Now the Hessian is in bold, so sorry about that. Anyway, so this function h, we're going to take derivatives. So the first term is the derivative of the function h, not the Hessian, with respect to the first random variable, which is L, right? So dh dl. That's what it is, right? So L is in the numerator, so it disappears when you take derivatives. And so on and so forth, right? The second term is dh dd, the third dh df, the fourth dh dv. Okay, that's the gradient. And there are formulas. We haven't evaluated yet, so that's why we have formulas. For the Hessian, the same thing. Let's take let's take this for example. So this one would be the second derivative of the function h with respect to, all right, so it's the first row, so the L, and it's the third column, so the third variable is f, the L, the f. All right, so that should be that derivative. And yeah, and they're all, and you see it's symmetric, so this should correspond to this one too. Okay, so it's not difficult, right? We know how to take derivatives. It was just tedious. There's so many of them when you have, okay? And then we evaluate at the mean values, right? So using these numbers for each of these variables, okay? And you get your 2 matrices. All right, and then you're golden. You just have to apply those equations. So hopefully, these step by step would ease the pain of doing that. All right, so make sure you know how to go from the equation to these numbers based on the Hessian matrix. Okay, so here we have mean and the variance. And again, second order approximation for the mean, first order approximation for the variance. All right, and then a typical question would be, what is the probability? So that's part A. Part B is, what is the probability that H is greater than, let me say 4, just to say something. Okay, so here's where you wave your hands. Here's where you kind of say, we don't know the exact distribution of H, so we can only approximate it. So what would be a good approximation that you can do based on this formula? Okay? Now, since you see product or ratios, then one should try to do the log normal approximation, right? The central limit theorem for products. That's what I would do in this case, just because we have a product. So we're in the case of a log normal probability computation when we're given the mean and the variance. Okay, so in this case, I would use the CLT for product, so the log normal. Okay, so here H is log normal, right? Now you need to compute the parameters, right? These two guys. But for these, we go back to the log normal section to see how to compute these two parameters when we're given the mean and variance. Okay? And then we can compute that probability. Very good. This is the same example as before, but we're going to add correlations between D and F and F and V and F. D and F and V and F, okay? And hopefully you'll be able to get these two numbers, all right? Okay. Very good. Now we're up to, this is actually the last section before we start talking about statistics, okay? So in this section, we're going to apply what we know about functions of random variables, okay? So, because in statistics, actually we're going to use these two distributions that we're going to discuss now. And both are functions of other random variables, right? That's why we did this chapter, actually, to understand these two functions. Because again, they're the main functions that we use in probability. They're the main distributions we use in probability. All right, let's start with the chi-square distribution with our degrees of freedom. All right, for the chi-square, let me start right here with this fact. And this is the part where the function of random variables comes in. Okay, so when you have a random variable x, that is the sum of the y variables, and the y's are all independent standard normal random variables, okay? So this is the chi-square distribution. It's whenever you add up, in this case, r independent standard normal random variables, and you square them, right? So it's a y square. And that's the function g in this case, right? It's going to be the sum of the squares of all these random variables. Now the reason it appears so much in statistics is because the sum of squares of normal variables, looks a lot like the errors that we're going to have when making predictions. So it's going to appear all the time. All right, so that's the chi-square distribution. It's the sum of r normal variables squared. All right. So if we apply the formulas that we learned in this chapter, we would find that that is the PDF of Z in that case, right? So we did the sum of, remember, two exponentials or two Poisson variables, right? Now, to do n random variables, we didn't do it, but we could apply the same method. That's the important thing, right? It's the same methodology, the same theorems with the absolute values and everything. Maybe we can do it during class. Okay, you don't need to learn that PDF. We're gonna use probability tables, such as this one. Let me see if I can click on it. And they work a lot like the normal table, but let's just take a quick peek. We're going to use them when we talk about statistics, but they're probability tables, very similar to the other ones, to the standard normal, which is the other one. Okay, so that's your chi-square distribution. Good idea to remember its mean and variance, R and 2 times R, but to be honest, we're not going to use much of it. All we're going to use is this table, but it's important for you guys to understand where it comes from. And it comes from being the sum of squared of standard normals. Okay, so this how it looks like. So when R equals 1, it looks like the exponential distribution, but for others, it kind of tends to the normal distribution for a big value of R, right? So these are the kind of shapes you get with this guy. All right, now we could do it for R equals 1 to see the proof, right? And that's a direct application of the formulas we just learned. Right, so this looks like an example on the previous section. If x is normal 0, 1, what is the distribution of x squared? Right, and it's going to be chi-squared with 1 degree of freedom, with R equals 1. Yeah, degree of freedom is just the name of the parameter for the chi-square. Right, and that's what's important. Right, so this is the PMF of the standard normal right here, right? And we have two roots in this case, square root of y and the negative. So this is what you get, and this would be the chi-square distribution for 1 degree of freedom. Now we can do it for more. It's a little bit more involved, but just to give you an idea. Okay, the other thing that's good to know about this distribution is that if you add 2, then the result is going to be also chi-square. And it's very easy to see because if you recall, the definition of chi-square is this one, right? That's the definition. So if you're adding 2, so if you're adding 1 with, R degrees of freedom, plus another one that has S degrees of freedom, or J squared, right? Both from I equal 1, right? This is just as one summation from I equals 1 to R plus S of yj squared, right? And that is going to be the chi-square with R plus S by definition. It's a very simple proof. Okay? Very good. All right, the other distribution we're going to use a lot, probably more than the chi-square, is the student's t distribution. Okay, and this appears as the ratio of two random variables. One is a normal 0, 1, again, so u in the numerator. And then in the denominator, we're going to have a chi-square with r degrees of freedom, v, divided by its degrees of freedom, r, and everything in square root. Okay? So that's going to show up a lot in statistics, and So this ratio turns out to be called the t distribution, the t random variable, defined like that. Okay, and that's the symbol for the t distribution, right? Like this is the symbol for the chi-square, right? So just t, and r is the same degrees of freedom here, which is, yeah, the degrees of freedom of the chi-square. Okay, so applying the same concept in this chapter with the absolute values and all those inverses and everything, we obtain this PDF, which you don't need to memorize. I don't even memorize it, because again, we're going to use tables to look up the necessary values. Okay? Very good. All right. These are the mean and variance of 0 and t. So one thing to note is that when the degrees of freedom tend to infinity, and infinity in practice is like 20 or 30, then it turns out that the t distribution tends to the normal 0-1 distribution. So this is shown here. So the normal 0-1 is in red, so it's the highest curve up here. That's the normal 0-1. And all the others are t distributions with increasing degrees of freedom. So from the blue one with 1 up to, you see, so the r equals 10 is already pretty close to the normal distribution, right? Okay. And with that, my friends, we have finished chapter 5. Congratulations. All right, so let's start with chapter 6. Finally, we're starting to talk about statistics. All right. So let's talk about normal random samples. So statistics, the main assumption is that the population random variable of interest, we're going to call it x, is normally distributed. Okay, so like in the figure, what is it, about blood pressure, right? So it's the population in this country, and then you take different samples, okay, of different number of people, you see. Now, each sample, you can consider it as a random vector, and each person will have its own random variable. In this case, the blood pressure is going to be xi, so we might as well put a subscript here. xi is normally distributed, all right? And then I is the, in this case, the person number in the sample. Okay, so what we're saying in that assumption is that everybody comes from the same population. So that mu is going to be the mean blood pressure, and sigma squared is going to be the variance of that. And it's the same for everyone. The difference is that every sample point, every xi, is a different realization of this random variable. All right, so these parameters are unknown and deterministic. All right, so mu and sigma squared are unknown, so the best we can do is estimate them. They're deterministic because they're constant. They're not considered random variables. Okay, mu and sigma squared. Okay, and the role of statistics is to estimate these guys, mu and sigma squared, for the most part. And then using those estimations to answer many questions. So that's what we're going to do in these two chapters that come, is ways to estimate mu and sigma, these parameters, and answering important questions about the population. All right, so the notation is going to be the same as we've been using the last couple of chapters. So the bold notation is the vector, right? So these are sample sizes. Now, recall the difference between uppercase and lowercase, right? So as a random sample, a realization of a random sample would be lowercase numbers, right? Because lowercase are realizations. Okay, and the random vector, capital bold X, represents the random variables themselves. All right. So remember, uppercase means it's like the name of the random variable, and lowercase is the particular number for that particular realization, right? Okay. Another important assumption is independence. Okay. And so all the xi will be independent, and also we're going to say that they're identically distributed, and that means that they all have the same distribution. In this case, normal mu sigma squared. And we're going to use the symbol IID right here. So that means that all the xi's in this population, or in this sample rather, come from the same distribution, normal mu sigma squared, and they're independent. Okay? So that's what the wiggle and IID mean. Alright. Now, these two are probably the most important estimators that we'll be using. One is the sample mean, x bar, and the other one is the sample variance, s squared. Okay? And it turns out that with these two random variables, we're able to build all the classical statistics that we're going to learn. Alright? So it all starts here. Okay, so capital X bar is the random variable representing the sample mean. Okay? So it's just the average, right? But notice that it's in capital letters, so it means that for each different sample, you're going to get different numbers. Right? Now, by the formulas for mean and variance of linear combinations, we know that the sample mean has mean mu and variance sigma squared, right? So that's important. We've seen that before. Let's show it one more time real quick. So that the expected value of x bar is mu. Please do it yourselves. Right, so you take expected value of both sides, you see that you're going to get mu. Let me do the variance of x bar. I know we did it, but it's so important that let's do it again. Alright, so it's going to be the variance of that sum, right? Okay, so the variance, 1 over n is a constant, so it comes out squared. 1 over n squared. Then you have the variance of the sum, right? And if we recall the formula for variance of linear combinations, the first term is the sum of the variances. Remember the diagonal terms? Okay, so it's going to be the sum of the variance of the xi's. And then since they're independent, there's no covariances. So that's it for the variance. And then all of these guys are sigma squared by assumption, right? The assumption is that they are IID. That means that they all have variance sigma squared. Right? And then this summation is from 1 to n, so it's going to be n times sigma squared divided by n squared, which gives you sigma squared divided by n. The variance, okay? Now, the result is really important because it shows you that the larger the sample size, the smaller the variance of x bar. Right? And at infinity, you could say that the variance is 0. And we're going to call that the law of large numbers, as in the next couple of slides. All right. Now, for the sample variance, that's the formula we're going to use. The first line there. Now, you might notice that the variance so let me say a word about the variance of x here, which is sigma squared, but it's unknown. So our basic estimator turns out to be s squared like that. Now the n minus 1, we're going to explain in a minute. Now, But remember that the variance of x, just by definition, is the expected value of xi minus mu, right? Square. Right, that's the definition of variance. Now, we've said many times that the expected value is like the average. So one could say that this is approximately equal to the average of that. So 1 over n of the sum of xi minus mu squared. Right? Which is almost the formula we have for a squared. So there's two differences. One is here we divide by n, and here we divide by n minus 1. Now we're going to explain that probably in the next subsection. Alright, now the other difference is that the formula of variance needs mu, so the real mean of x. Since it is unknown, we're going to use x bar as a proxy for mu, right? Because we know that the best estimator of mu is x bar. Okay, so that's why that's where this formula comes from, let's say. Okay, so it's kind of it's similar to this equation right here, right? But with these two differences. And one is that we don't know mu, so we replace it by x bar. And the other one is we divide by n minus 1. And that's going to become clear in a minute. But basically, just let me tell you, all you want from, the first thing you want from an estimator is that it be unbiased. And these are unbiased estimators. Now, bias or unbiasedness means that when you take the expected value, for example, of x bar, you recover the original parameter, right? So if I take expected value of x bar, it's 1 over n, I guess I'm doing it for you now, right? 1 over n summation and then expected value of xi's. Now, because they're all IID, they all have mu, okay? And so if you do that summation, that's mu, right? So this shows that that x bar is unbiased, because when you take the expected value of x bar, you obtain the parameter that you were trying to estimate. Okay, so and that's going to be the reason why we're divided by a minus 1 and not n. All right. So again, these are the two estimators we're going to be using throughout, and this is where all the statistic is built up from. Alright, now the shortcut formula for the variance is this one in the bottom, and right, so it's the sum of the xi squares minus n times x bar squared. Many times this is easier to compute than this one's easier than the original. But of course both give you the same formula. And if you have it in your calculator, which most of them do, you can use that as well. Here's the proof of the shortcut formula. Please go through it. Alright, and then let's talk about the law of large numbers. So it's simply the fact that since x bar, the sample mean, is distributed normal with mean mu and sigma squared divided by n as the variance, and this is the important thing, right? It's because it's divided by n, then we have this limit. As n goes to infinity, x bar tends to the real mean. Okay, so that's a result that is asymptotically true. So you need n to be really infinite to be true, right? But in practice, we never take infinite samples. So we're always going to have an error associated to our estimations. But the law of large numbers is reassuring because it says the larger the sample, the more accurate your estimations will be. Okay. Then let's define standard error. When you say standard error, it's going to be simply the standard deviation of the sample mean. That's really what it is. Okay, so it's going to be sigma divided by square root of n, if you know sigma, which you never do. So typically the notion of standard error is going to be s divided by square root of n. Right? Okay. This is an example. Please go through it to make sure you're able to calculate means and variances. So here you can use the shortcut formula. Remember, it was the sum of the xi squared, now in lowercase because they're numbers, they're realizations, right? So that sum minus n times x bar squared. Now this sum is by itself. It's not, yeah. Okay, so this should be a faster calculation than the other one. All right, so that's the sample variance, and that's the standard error. All right. All right, so we're ready to build up the theory. Basically, we're going to define 3 new random variables. Okay, the z, t, and c squared statistics. All right, and it turns out that with these 3 random variables, we're able to do everything we need to do in statistics at this level, right? So that starts from here. Well, I said this again, I guess. All right, let's start with the z statistic. The z statistic, it's like the z random variable we saw before. It's a normal 0, 1 random variable, okay? But in the context of statistics, it corresponds to standardizing the distribution of the sample mean, right? Because we know that the sample mean has normal distribution mu sigma squared divided by n, right? Now we standardize, if we compute the z-score of the sample mean, this is what we obtain, the famous z statistic, right? Because we're divided by the mean, mu, and, subtracting the mean and dividing by the standard deviation of the random variable, which is sigma divided square root of n, right? And that's how we compute z-score, right? We subtract the mean and then divide the whole thing by the standard deviation of the random variable. Okay, and this has the normal 0, 1 distribution by definition. Okay, and then given these statistics, turns out we can do a bunch of things. All right. Now the problem that in practice sigma squared is not known. So the solution is replaced by s squared. That's the best estimator. But then it turns out that we cannot use the z statistic anymore, and we're going to use the t statistic, which will be defined in the next couple slides.